Okay, we're discussing tension, and tension is something we're already familiar with as a concept, right? If you pull on a rope or a string or a thread, you take it from being sort of slack, right, to something that's quite taut. And if you pull hard enough, you might cause it to snap, or you could maybe stretch it or something like that. But tension, right, we already have an idea of what that means. However, in physics, it has much the same meaning, but we want to understand how it translates forces from acting on one object to another. And so, just as sort of a toy example, we're going to take this vector art gentleman here, who is using a rope to try to pull over a tree. Because, I don't know, he's very confident, or maybe the tree looks sickly or something like that, and he thinks he can just pull it right over. Okay, but at least at the moment, we're going to say that he's failing to do this, so the acceleration of him and the tree, and thus the rope, are all zero, because they're all attached to one another, and so they must be experiencing the same acceleration. If one is at zero acceleration, then the others are. Let's take a look at the forces that we would expect to see here. So, actually, maybe green's not a good color. Let's go with black. Okay. So, the guy here is going to have quite a few forces acting on him, right? And the way that you want to enumerate forces when you're doing a force diagram or a free body diagram is to consider first whether gravity is acting, and since we're on the Earth, since he's pulling on a tree, then we're expecting gravity. That's our one force at a distance. And then we're also considering all of the other contact forces that could be acting on him. And that really narrows down the number that we could have, because only the things in contact with him can possibly exert forces on him, right? Kind of by definition. So first, let's put in the force of gravity. Okay. There we go. And if gravity is pulling him down and yet he's not accelerating down towards the center of the Earth, right, the ground must be holding him up. So we have some normal force from the ground. And then what else? Well, he's certainly hauling on the rope, and so the rope is going to haul back on him. Equal and opposite third law pair. And so for him, we would have a force of, let's just call it F rope. And finally, if these were the only forces acting on him, we would expect him to be accelerating in the direction of the force of the rope. We know that that's not taking place, and what could possibly be counterbalancing that? Well, the force of friction, which also is going to be parallel to the ground between his feet and the ground. And we'll put that sort of down here. All right, so the force of friction, static friction in this case. All right, so we've taken care of all the forces of the ground acting on him. We've taken care of the force of the rope acting on him, and we've taken care of the one force at a distance that we have, gravity. So we're done, right? Nothing else is touching him, so there are no other contact forces. Okay, and there it is in nicer typology. Okay, so we've got F sub n, we've got the rope, we've got the force of friction, we've got gravity all acting on him. Great. All right, we know that they all have to cancel out, because if acceleration is zero, then the net force, according to the second law, also has to be zero on this gentleman. Okay, let's look at the other object on the other side of the rope, which is the tree. And the tree, well, it's a little bit weird. It's not like the tree is just sort of resting on the ground, right? Its roots are all sort of throughout it. So the normal force in this case, I suppose you could think of as some sort of weird vector sum of all of the bits of ground acting on all the different bits of roots, but still there's some upward net force from all of those little bits of force that would amount essentially to the same thing, this normal force that holds up the tree against the force of gravity acting downward on it. And then we, of course, if the rope is pulling on the tree, and we know it must be, then the tree is pulling back on the rope. So that's another third law pair, sort of on the other end of the rope. And so the rope is pulling this way. Okay. And lastly, well, something must be keeping the tree in place. And in this case, you could talk about friction between the roots and the earth. You could also talk about some sort of elastic force. So if he's sort of bending the tree a little bit, trees tend to spring back up. And so you could call it force of friction. You could call it the elastic force, Fe maybe for friction and elastic, but something that's resisting the pull of the rope, which effectively is the pull of the guy on this tree. All right, and all of those have to cancel out. So we see that there. Now you'll notice we've got a situation where on one end we've got the rope pulling on the tree to the left, and on the other end we've got the rope pulling on the guy to the right. But the guy and the tree aren't directly touching one another, so how can we work out that that must be sort of a third law pair, that those have to be equal and opposite? Well, it's not just the gentleman and the tree in this interaction, it's also the rope itself, right? And if we assume the rope's mass is pretty negligible, right? I mean, technically there'd be like some little downward force of gravity or something like that, but mostly the dominant force here on the rope is going to be the guy pulling on the rope, which has to be the third law pair with this force, right? Because the rope pulls on him, equal and opposite. And on the other end, well, there has to be a force of the tree on the rope, which has to be in this direction. Okay, and again, this and this would be a third law pair, right? Because it's the rope and the tree interacting. And so we can see that these two forces that are being exerted on the rope by the tree and the guy respectively, those have to be equal and opposite because the rope is not accelerating, okay? And this turns out to be a general statement that when you have a taut piece of rope or chain or thread or whatever fiber it is connecting one thing to another, then the tension force in that rope translates equally to both ends of that rope, okay? So this technically gets a little weirder when you start considering the mass of the chain or the thread or the rope and all that kind of thing. The model gets a little bit more complicated, but it is an excellent approximation unless you have a very, very heavy chain or something like that, that the tension force created by, in this case, the guy pulling on this end is translated all, 100 newtons or something like that to be pulling on whatever is connected to the other end of that rope, in this case, the tree. All right? So that's the idea behind the tension force. The tension force in this example would just be sort of this force that is acting on the rope and thus acting on the two things that are attached to this taut rope. And what we're going to do in the next video is we're going to take tension and we're going to apply it to another two-dimensional forces problem. So we have that to look forward to. And I'll leave this video here. Please enjoy.